Hey everyone, and welcome. Today we are diving deep into the absolute heart of computer science, algorithms. Seriously, understanding this stuff is what takes your code from just okay to actually great. So let's jump right in.
Okay, so think about this for a second. What on earth could making a simple cup of tea possibly have in common with the incredibly complex tech that powers Google Maps? The answer, believe it or not, is the same, and it's the key to everything we're talking about today: an algorithm.
So here's our game plan. First, we're going to break down what an algorithm even is. Then we'll figure out how to measure if one is any good. After that, we'll dive into two of the most important jobs they do, sorting and finding data. And we'll wrap it all up with a clear path so you can start mastering this on your own. All right, first things first, let's tackle this word algorithm. It sounds super technical, right? But I promise you, it's a concept you're already an expert at using every single day. So, what is it really? At its core, an algorithm is just a recipe. That's it. A simple, step-by-step set of instructions to get something done. And here's the most important part. It's about the logic, not the language. You could write the same algorithm in Python, in JavaScript, or just scribble it on a napkin in plain English.
And this is the perfect example. Making tea is totally an algorithm. You follow a specific sequence of steps in a specific order to get a predictable result: a cup of tea. Boil the water, add the leaves, add milk, pour, and serve. Boom, you just ran an algorithm. See, you've been doing this your whole life.
Okay, so from tea to tech, let's see how that same simple idea powers pretty much everything we do online. Every time you sort your email, search for something on Google, stream a video, find a route on a map, or get a recommendation from Netflix. Yep, that's all being driven by some very clever step-by-step algorithms working behind the scenes. All right, so we get what an algorithm is, but are all algorithms created equal? Not even close. So how do we figure out which one's good and which one's, well, not so good? For that, we need a way to measure them, and it's called Big O notation. Think of Big O notation as the official report card for an algorithm. But here's the thing, it doesn't measure speed with a stopwatch. That can change depending on the computer. Instead, it measures how well the algorithm scales. As you feed it more and more data, does it slow down just a little bit, or does it just fall off a cliff? It's all about that growth trend. Let's look at this report card. These are the grades you'll see most often. O1 is the A+, the holy grail. It means performance is always the same, no matter how much data you throw at it. ON is linear. That's pretty good too. But then you get to ON squared. Yeah, that's where things get ugly really fast. And on the amazing end, you have O log n, which is incredibly efficient. And the simple rule, the lower the growth, the better. Always. And if you're a visual person, this chart says it all. I mean, just look at that difference. The linear one grows at a nice, predictable pace. But that quadratic one, it just explodes. For a tiny bit of data, they might look pretty similar. But as you add more, the performance difference becomes absolutely massive. This is exactly why choosing the right algorithm is so critical. Okay, let's put this theory into practice with one of the most fundamental problems in all of computer science: sorting. How do we take a total mess of information and bring some order to it? But why bother? Why is sorting so important? Because sorting is the gateway to efficiency. As soon as your data is in order, finding things becomes dramatically faster. It helps you organize, clean up, and just generally optimize everything else you want to do. So, let's start with a classic, bubble sort. It's really easy to get your head around. You basically just shuffle through the list, comparing two items at a time and swapping them if they're out of order. You do this again and again and again until the biggest values bubble up to the end. It makes sense, but that O of n squared rating tells you it's painfully slow for big lists. Now, let's contrast that with a real powerhouse, merge sort. This thing uses a super clever strategy called divide and conquer. It just chops the list in half, then chops those halves in half, and keeps going until it has a bunch of tiny, easy-to-sort pieces. Then it masterfully merges them all back together in perfect order. It's a much smarter way to work, and its O(n) log n rating means it's incredibly fast and efficient. Okay, we've done the hard work. Our data is sorted. So what was the point? Well, this is the payoff, finding what you're looking for at lightning speed. Let's look at the science of the search. So here's the challenge. Imagine a phone book with 1 million names, but they're all jumbled up in no particular order. Your task, find one specific name in that giant mess. Go.
Okay, you've basically got two ways to do this. There's linear search, which is the obvious, brute force way. You start at page 1 and check every single name until you find the one you want. Simple, but slow. O of N. Then there's binary search. This is the clever way, but it only works if the data is already sorted. It's like a guessing game. You jump to the exact middle of the list and ask, is my name in the first half or the second half? Then you throw away the half you don't need and do it again. It's an amazing O of log N. And this is where it gets absolutely mind-blowing. With that linear search, if you're really unlucky, you might have to check all 1 million names. 1 million steps. But with binary search, because you're cutting the problem in half every single time, you are guaranteed to find that name in about 20 steps. 20! From 1 million down to 20.
Yeah, just let that sink in for a second. 1 million versus 20. That right there is the incredible, game-changing power of choosing the right algorithm for the job. It's the difference between something being impossible and something happening in the blink of an eye.
Okay, so if your mind is sufficiently blown and you're thinking, I need to learn this stuff, where do you even begin? It can feel like a lot, I get it, but there's actually a really clear path to follow. Here's a pro tip for the order you should learn these in. Start with the simple stuff, the basic searches. Then tackle the simple, kind of clunky sorts like bubble sort. As you go, you'll start to see the patterns. You'll understand why one is better than another. And you'll naturally build up your intuition for the really powerful, clever stuff, like merge sort. So, at the end of the day, what have we learned? That algorithms aren't some scary, abstract thing for geniuses. They're just smart recipes for solving problems, and they're the secret to making things fast, efficient, and powerful. So, I'll leave you with this thought. Now that you understand the logic, what problem are you going to solve first?